All right, so this is the second part of chapter 8. So here you are going to learn few more things about rotational motion. But if you understand the thing that we already discussed in last lecture, it would be not too bad. I mean, it's basically comparing some quantities with the linear quantities. Okay, so that's it basically. Okay, for example, the first thing we are going to learn is a rotational equivalent of Newton's second law. Okay, so in last lecture you learned that the rotational equivalent of force is torque. So let me write down. Okay, so we already learned that rotational equivalent of L, that means the linear displacement, is theta. Okay, rotational equivalent of velocity is omega, angular velocity. Alpha, sorry, this is A. Rotational equivalent of acceleration is angular acceleration. And then we see that the rotational equivalent of force is torque, right? Tau. So this we already learned. Okay. Now here we are going to learn that similar to the Newton's second law, we already learned earlier, F equal to ma, we can write a rotational equivalent of Newton's second law, and it would be something like this. So F is replaced by tau, okay, A is replaced by alpha. Now we need something for rotational equivalent of m. Okay, so m for the time being, let me replace by I. Okay, and let me call it moment of inertia. Moment of inertia. Okay, or it's also called rotational inertia. Okay, so this also called the rotational inertia or the moment of inertia. Okay, for the time being, just remember that, and then we are going to determine the mathematical relationship between I and, I mean, mathematical definition of I, or the moment of inertia. So this is the Newton's second law. Okay, when rotation involved, the Newton's second law is this one. So tau equal to I alpha. Okay, where tau is the torque, which is the rotational equivalent of force, and alpha is the angular acceleration, and I is the rotational equivalent of mass. We call it rotational inertia. Okay, and this law is the rotational equivalent of Newton's second law. Okay, tau, the net tau equal to I times alpha. All right. Now, to determine the mathematical definition of moment of inertia, let's consider this diagram. Okay, and this diagram tells us that we have an object of mass m. This is the object, mass m, and it is traveling in this circular, I mean, it is rotating about this axis and traveling in this circular path. Okay, all right, and the radius of the circular path is r. Okay, now let's say you apply a force F on this object. Okay, now from the Newton's second law, we know that when there is force, there is some acceleration. So it will be a tan in this case, because this is tangential. This force is tangential to the circle, I mean, at this point. So the acceleration, the linear acceleration that we have here will be tangential acceleration, right? So from this diagram, we can say from the Newton's second law, Newton's second law of motion, that F equal to ma tan. Okay. Now, in last lecture, remember that we derive an equation for a tan and alpha, right? A tan was equal to r alpha. So if I substitute A10 equal to R alpha, this looks like this. So F equal to M R alpha. Now let's multiply both sides by R. Okay, so it will be M R square alpha. So we multiply both sides of the last equation by R, we get this. Okay. Now you know that sine 90 degree equal to 1, right? So I can write that equation as this. Okay, so because it is 1, so multiplying by 1, multiplying something by 1 is basically the same thing. So we did not change anything basically for right. So it's basically exactly the same. So we explicitly write sine 90 degree, but sine 90 degree is equal to 1. So it's exactly the same thing. So what we did, we multiply sine 90 degree here on the left hand side to write is as tau, right? Because tau equal to R F sine theta. And here you see that this is R. You apply a force here, and the angle between R and F is sine 90 degree. So because RF equal to, RF times sine 90 degree equal to tau, so we can replace the left hand side as tau. So tau equal to M R square alpha, right? And then we already know that tau equal to I alpha. So we have tau equal to I alpha, we have tau equal to M R square alpha. So if you compare these two equations, you see that I can be written as M R square. So the moment of inertia of a single particle is mass times radius square. Okay. So similar to the mass, it's a scalar quantity. The moment of inertia is a scalar quantity. And from this equation, I equal to mr square, we can write the unit of I. The standard international of unit of I is kilogram meter square. So kilogram from mass and meter square from r square. Okay. So the last equation we derived is for a single particle. Okay. And yeah, so here is I equal to mr square. Now what about if we have more than one particle? Okay, if we have more than one particle, then we have to individually determine the moment of inertia. So for example, for this picture, we have several particles. So M1, M2, M3, M4, M5, and so on. And the corresponding radius are R1, R2, R3, R4, and so on. So for M1, the moment of inertia is m1r1 square. For m2 it is this, and so on. So the moment of inertia for the whole system will be this, the sum of all the moment of inertias for all the particles. Okay. All right. And it's a scalar quantity, and the standard international unit is kilogram meter square. All right. Okay. Now, there are some standard particle. To solve some problem, we need to understand, we need to actually use the moment of inertia, for example, for this kind of standard particle, standard object. Okay, so for example, this is a ring. Okay, and this ring is rotating about the center. Okay, and this ring is rotating about this. This is cylindrical disc. Okay, it's rotating about the center. Okay, so for many problem, Okay, at least we will be doing some of the problem where you will see we need to use the moment of inertia for this standard particle. Okay, now to determine the moment of inertia for these particles, we need to use calculus. Okay, but this is algebra based course, so I'm not going to introduce calculus and show you how to derive these quantities. Instead, we are going to use this chart. Okay, so if I ask you in exam, I will be giving this chart. Okay, so and then you can use directly from this chart. Okay, all right, so these are the standard moment of inertia for this standard object. For some of the problem we are going to use these, okay, at least few of them. Okay, so that you will understand what is what. Okay, but I want to show you, I mean, even I am not going to derive this from the calculus, but I want to show you from this simulation. Okay, so this simulation basically shows us the moment of inertia. For example, we probably use okay, so here this. Okay, so you see this is rotating about its center, and the moment of inertia for this disc or a cylindrical object, I mean solid cylindrical object, is half mr square, where m is the mass of the object and r is the radius. Okay, now if you have a hollow cylinder, something like this, you see it is different. It depends on the inner and outer radius. Okay, another thing I want to show you is, for example, a spherical object. Okay, so for a spherical object is a solid sphere, and if it is rotating about its center, the moment of inertia is 2/2/5 mr square. But if it is a hollow, okay, so you see that it is different. For empty, I mean, if the inside is empty, then the moment of inertia is 2/3 mr square. If it is solid, it is 2/5. Okay, so another thing I want to show is that this ring. Okay, so you see that for this ring it is mr square if it is rotating about its center, but if it is rotating about this, it's different. Okay, so what I wanted to show you here is the moment of inertia depends on the axis of rotation. If you change the axis of rotation, moment of inertia also changed. Okay, of course it depends on the mass and also the radius. At the same time, it also depends on the axis of rotation. Okay, so I mean, if I ask this kind of question during exam, I will be giving the chart, and from the chart you have to choose the correct one. Okay, so for example, if I give you a solid cylinder, a solid sphere, you have to use 2/5 mr square. But if I give you a hollow or inside empty spherical shell, then you have to use 2/3 mr square, and so on. All right. Now, a few more things, but these things are not too difficult. Okay, kinetic energy. So earlier we learned that the kinetic energy is equal to half mv square, right? Now, when rotation involved or rolling involved, right, we may have both rotational and translational kinetic energy. Okay, so we need to define that. So you already know that translational kinetic energy will be something like this, half mv square. But what about the rotational kinetic energy? Rotational kinetic energy can be written from this equation. Okay, and that is equal to this. Okay, so here you see that I mean m is replaced by the rotational inertia, and velocity is replaced by angular velocity. Okay, earlier in the first slide you see that the angular equivalent of mass is the rotational inertia, and angular or rotational equivalent of velocity is angular velocity. Just by replacing the angular linear quantity by angular quantity, you can write the kinetic energy for the rotation. Okay, all right. And the unit is again a joule. This is a scalar quantity because all energies are scalar, and all energy should have the same unit, so its unit is also joule. Okay, now when we have if rolling if the motion is rolling motion, as you know that both translational and rotational motion involved, then the kinetic energy is the sum of the translational kinetic energy and the rotational kinetic energy. And you see that the equation is something like this. Okay, now in chapter 6 we solved some problem by using the conservation of energy. So in chapter 6 we neglected the rotational kinetic energy because rotational, I mean, we did not consider the rotation over there. But here we probably solve a few problem where we have to use conservation of energy. So if we use conservation of energy where rotation involved, then make sure you use both kinetic energy. Okay, rotational kinetic energy and translational kinetic energy. Okay, so we'll solve some problem, you will see that. And while solving the problem, it probably help you to better understand. Okay, now in chapter 6 we learn about work done. Okay, so the definition of work done was W equal to R F cosine theta, right? So let's consider a very, I mean, it's basically D F D cosine theta, right? So let's consider a very simple case, okay, where W equal to DF, where the angle between D and F is 0 degree. Okay, so let's consider this simple case. Okay, so here D is the displacement, F is the force. Okay, so we can write in analogy with this equation, the work done in rotational case will be, so F should be replaced by tau and D should be replaced by theta. Okay, so basically delta theta, because delta theta is the displacement. So tau delta theta is the work done by torque. Okay, so you see that this is the displacement and this is the force. Okay, so here it's the same thing. This is the angular displacement and this is the angular or rotational equivalent of the force. Okay, all right. The last thing here we are going to learn is the angular momentum. Okay, so in last chapter you learn about the linear momentum, and you can simply using the definition of linear momentum, you can write the mathematical definition of angular momentum. Okay, so we use symbol L for angular momentum. Okay, so if you remember, the linear momentum or the momentum was P equal to m times V, and the relationship between the force and momentum was this one, F equal to delta P delta T. So in analogy with these two equations, you can write the angular momentum is L equal to I omega. So here you see that I is replaced by, I mean, M is replaced by I and V is replaced by omega. Okay, and the same thing, F is replaced by tau and P is replaced by angular momentum. Okay, so you see this is very similar to the linear momentum. Okay, so it's a vector quantity similar to the angular linear momentum. This is a vector quantity and the standard international unit is So for this one, it is kilogram meter square, and for omega, it is radian per second. Okay. So altogether, it gives you kilogram meter square per second. So when we have more than, when we have other units with radian, we don't basically use radian. So and radian is basically just number. Okay. We use radian only for omega and alpha. I mean theta, omega, and alpha. And wherever we, in other cases, we basically neglect that. For example, here it should be kilogram meter square radian per second, but you see that we neglect radian here. So you can use radian here, but it doesn't matter whether you use radian or not. Okay, so it's basically the same thing. Okay, normally we do not use radian for angular momentum. Okay, so the standard international unit for angular momentum is kilogram meter square per second. So similar to all other angular quantities, okay, all other vector angular quantities, clockwise rotation means negative sign, okay, and counterclockwise or anti-clockwise means positive sign. So when object rotates counterclockwise, the convention is the positive sign. We have to use positive sign, and for clockwise rotation, we have to use negative sign. Okay, and the last thing is the conservation of angular momentum. So in last chapter, you learn about the conservation of linear momentum. So similar to the linear momentum, conservation of linear momentum, we have conservation of angular momentum. And it says that if the net torque on an object is 0, the total angular momentum of a system is constant. Okay, it does not change. Okay, we write something like this: L1 equal to L2. So I1 omega 1 equal to I2 omega 2, and it is constant. Okay, so for example, here this lady is the system here. Okay, so in this position, the I and omega are different than I omega here. So let me call it I1 omega 1, I2 omega 2. Okay. Okay, so here you see in the first picture, okay, here I is large. Okay, so I large because here m r square, right? R is large, so because we have, this is r for some particle, at least for some particle. So if this is the rotation axis, so this is r. Okay, so I is large, so to have the conservation of angular momentum, omega should be small here. Okay, so I is large, omega should be small. Okay, but in this case, I is small, so omega is large. Okay, so what it tells us that the angular momentum is conserved if there is no net torque act on the object. Okay, so if it is, then I1 omega 1, which is the definition of the angular momentum, I omega is constant. For the first picture, I is large, so omega should be small. In this picture, I is small, so omega should be large. Okay, so with this, I'm going to stop, and we are done with this chapter 8. Okay, in next class, we are going to solve some problems.